You know, it is incredibly easy to look at massive industrial infrastructure things like towering offshore oil rigs in the North Sea or miles of pipelines snaking across deserts and just assume they are indestructible.
Oh, absolutely. I mean, we're talking about thousands of tons of solid forged steel.
Right, exactly. You stand next to one of these massive drill strings plunging thousands of feet into the earth, and you think, well, what could possibly take this down?
Yeah, you expect it would take a meteor or something.
Exactly. But when you look closer, past the heavy machinery and the sheer blunt force of it all, the real enemy isn't some massive physical impact. It's microscopic.
Hmm. It is relentless.
It is rust.
It's a hidden, silent war playing out every single day. We look at a skyscraper or a drilling rig and marvel at the architecture, completely taking for granted the sheer amount of chemical engineering required just to keep those massive threaded pipe ends from literally eating themselves alive.
Yeah, that invisible science.
Right, because when you are dealing with heavy industry, where a microscopic stress fracture from corrosion can cause a multi-million-dollar catastrophic blowout, preventing oxidation during long-term storage requires an entirely different level of science. I mean, standard protective oil simply does not cut it.
And that brings us to the mission of today's deep dive. Welcome in, everyone. We have a stack of notes and a very specific, highly specialized piece of industrial engineering to explore today.
Yeah, we're looking at a technical data sheet, or TDS, for a storage compound called Korr-Guard, manufactured by Jet-Lube.
Now, I know what you might be thinking, a technical data sheet for industrial grease. Really?
Sounds dry, I know.
It does, but okay, let's unpack this, because what this document actually reveals is a high-stakes molecular battle against decay.
It really is.
It's essentially a masterclass in how to build an unbreakable shield, and it completely flips the script on how we protect our most vital infrastructure.
To really appreciate the innovation hidden in this document, we first have to understand the baseline. We have to look at what the rest of the industry has been doing for decades.
Right, setting the stage.
Exactly. According to the text, the vast majority of corrosion-resistant greases on the market rely on a pretty standard generic formula. They take a base, usually lithium, aluminum, or anhydrous calcium.
And just for context here, anhydrous calcium just means a calcium-based soap that has been stripped of all its water.
Right, good point. So they take one of those bases and they create a standard grease.
And then to magically make that standard grease quote-unquote corrosion-resistant, the manufacturers treat it with a liquid rust inhibitor.
But the text highlights something really crucial about this industry standard. That rust inhibitor only makes up about 2 to 5% of the final product.
Wow, just 2 to 5%.
Yeah, so you have a massive tub of grease, and only this tiny fraction of it is actually fighting the rust.
And that small percentage is the fatal flaw, right?
Yeah, absolutely. That 2 to 5% inhibitor is oil-soluble, and it is surface-active.
Meaning what, exactly?
Well, in chemistry, surface-active means it actively wants to seek out and coat the metal. It wants to wet out on the steel surface. Manufacturers put it into the oil because it's cheap, it's easy to mix, and theoretically, the oil carries it right to the metal.
Which, I mean, that sounds good on paper. You want the inhibitor touching the metal, but I was trying to picture this while looking through our sources, and let me try this analogy out on you.
Go for it.
So the old way, the standard 2 to 5% additive way, is basically like using a wet sponge to keep a surface soapy.
Okay, I'm following.
The sponge itself is the grease base, and you soak it in soapy water, which is your oil-soluble rust inhibitor. You wipe the counter and it gets soapy. But eventually gravity, time, and heat win out.
Right, the environment takes over.
Exactly. The soapy water drips out, the moisture evaporates, and you are just left with a useless dry sponge sitting on a counter that is no longer protected.
That is spot on. Let's push that analogy even further because it perfectly illustrates the physics at play here. The sponge itself was never doing the protecting.
Right.
It was just a flawed delivery system for a liquid that was always going to escape.
Yeah.
In a pipe yard, when a steel pipe sits in the baking sun for months, the oil in that standard grease begins to bleed or separate from the thickener.
So the oil just runs off.
Exactly.
Yeah.
And because that 2 to 5% additive is trapped in the oil, it bleeds out right along with it. The protective barrier literally runs out of fuel.
Oh.
For long-term storage, that depletion is just a death sentence for the metal.
So the standard method is practically doomed by its own design, and this is the massive aha moment in the document for me.
Oh, absolutely.
Because in any grease, there is the oil, and then there's the thickener, often called the soap. The text makes a clear mechanical distinction here. It is the thickener, the solid structure, that actually adheres to the metal, not the slippery oil.
Right. What's fascinating here is that Jet-Lube looked at this and completely abandoned the wet sponge methodology.
They just threw it out.
They did. Instead of adding a little bit of liquid inhibitor into the separating oil, they engineered a way to chemically complex the rust inhibitor in high quantity directly into the thickener itself.
So they basically took the soap and wove it directly into the synthetic fibers of the sponge itself.
Yes. As long as the sponge exists, the soap is there. They have structurally bound the protection to the very thing that grabs onto the metal.
That is brilliant.
And the numbers back it up. The text notes that Korr-Guard's thickener content ranges from 19 to 25%.
Compare that to the standard 2 to 5% liquid additive. That is a massive jump.
It is. By massively increasing the quantity of the thickener and making the thickener itself the protective agent, additive depletion goes from being an inevitable failure to just a non-issue.
I am looking at the manufacturing notes, though, and, well, this process does not come for free.
No, definitely not.
The text mentions that this chemical complexing process, baking the rust inhibitor into the structural matrix, results in a, quote, significant yield reduction.
Yeah, that's a key detail.
It also says the actual percentage of the thickener depends on intricate processing variables. Are they just willingly sacrificing their own manufacturing efficiency here?
Well, yeah. In chemical manufacturing, a yield reduction means you're getting less usable product per batch because the processing variables are just so intense. It takes more time, more energy, and way more precision to force that much inhibitor into a solid matrix.
But they do it anyway.
Because they are willing to take that financial and operational hit on yield. The resulting stability is exactly what heavy industry pays for. I mean, a company drilling a deep water well doesn't care if the grease took longer to make.
Right, they care that their drill string doesn't shatter because of a microscopic rust pit halfway down the ocean.
Exactly.
Okay, so understanding the chemical theory, this idea of a structural high-percentage thickener, is one thing. But I want to know how this olive green petroleum and synthetic fluid actually holds up when the physical environment attacks it.
Oh, the torture testing.
Yes. Because the physical characteristics listed in this data sheet read less like a lab report and more like a medieval torture test.
The environmental metrics are punishing. They engineer this to survive scenarios that would literally liquefy or freeze a standard lubricant.
Let's translate some of these extreme numbers for you listening. So the dropping point, which is the temperature at which a grease loses its structure and becomes fluid enough to drip, is rated at over 392 degrees Fahrenheit.
That is intense heat.
Yeah, and the flash point, where its vapors can actually ignite, is over 430 degrees Fahrenheit. And its general service temperature ranges from a freezing -20 degrees all the way up to 425 degrees Fahrenheit.
Which basically means it is a highly stable matrix designed specifically to stay exactly where it is put, regardless of whether it is baking in a West Texas summer or freezing in an Alaskan storage yard. It won't freeze solid and it won't melt off.
Okay, wait, let me play devil's advocate here.
Okay, lay it on me.
I see those temperature ranges, and I see the salt fog and spray resistance test. The text says they tested this grease in a 5% sodium chloride environment at 100 degrees Fahrenheit, and it lasted for over 2,000 hours. Then they cranked it up to a 20% sodium chloride environment, and it lasted over 750 hours.
Right.
To put this in perspective for the listener, why subject a grease to what sound like boiling, salty hurricane conditions for months on end? Marine grease already exists. People have been putting grease on boat hulls for decades to stop saltwater corrosion. Why do they need this highly complex 2,000-hour specific formula?
That is a great question. If we connect this to the bigger picture, it really comes down to the difference between repelling water and surviving a chemical siege.
A chemical siege?
Yeah. See, standard marine grease is great at physically repelling water, but it is often just a standard grease base packed with those oil-soluble additives we talked about earlier. Under relentless pressure or over long periods of static storage, those additives still deplete and the salt water eventually penetrates the barrier.
Oh, I see.
The salt fog test is different. 2,000 hours in a 100-degree salt fog isn't just getting splashed by a wave. Drill strings and pipes are often stored in punishing coastal or offshore environments. It is a highly accelerated simulation of a steel pipe sitting on a dock in the humid, boiling Gulf of Mexico for years, just constantly bathed in a vaporized chemical soup.
And salt is an absolute catalyst for corrosion.
Right. Korr-Guard survives because the barrier isn't a thin oil film. It's a structural wall.
And the datasheet provides other specs that explain how it builds that wall. Let's talk about specific gravity and density for a second.
Oh, yeah, the physical weight of it.
Yeah. The sheet lists a specific gravity of 0.94 and a density of 7.85 pounds per gallon. Why does that matter to a worker out on an oil rig?
Because it means this grease is physically dense and substantial. If a torrential storm hits the pipe yard, the water doesn't easily wash the grease away. The grease physically displaces the moisture.
It just sits there like a rock.
Pretty much. The structural thickness is heavily quantified here, too. It has an NLGI grade of 0 to 1.
And for context, the NLGI scale measures how hard a grease is, right?
Exactly. A 0 is basically the consistency of brown mustard, while a 6 is like a block of sharp cheddar cheese. So a 0 to 1 grade puts this right in that soft, highly spreadable zone.
Okay, mustard-like, got it.
But then you look at its Brookfield viscosity, which measures resistance to flow. It rates between 42,000 and 75,000 centipoise.
So we are talking about something with the consistency of very thick molasses or maybe even a soft peanut butter.
Yeah, peanut butter is a good way to picture it.
It is spreadable, but it is incredibly dense. That thickener complex isn't just chemically neutralizing rust, it is physically barricading the metal against the elements.
But, that creates an entirely new problem.
What's that?
Well, lab tests are perfect controlled environments. The actual field is famously messy. If you have engineered a product that is basically an unyielding, incredibly dense synthetic wall of molasses, how do you accommodate the human element? You have tired workers out in the elements who actually have to apply this stuff to miles of pipe and eventually take it off.
Right, the practical application. Well, the guidelines show they engineered a surprisingly wide tolerance for that human element. If a worker is brushing it on by hand, the text dictates they can do so in temperatures ranging from 0 degrees to 150 degrees Fahrenheit.
This huge window.
It is. And if they are using a mechanized spray application, the window is slightly tighter, from 50 degrees to 150 degrees Fahrenheit. So you aren't fighting the grease to get it onto the metal.
And the real efficiency shows up when it's time to actually drill. Imagine a pipe that has been in storage for 2 years. It is heavily coated in this thick Korr-Guard, and it has a massive plastic or steel thread protector screwed onto the end.
Okay, picturing it.
When a worker in the field unscrews and removes that thread protector to connect the pipe to the drill string, the document notes that less than 5% of the storage compound is left behind on the connection.
Oh, wow, so it just peels right off.
Exactly. The bulk of it clings to the protector and comes right off.
That is incredibly convenient. The datasheet provides very specific, pragmatic advice for the workers here, too. It says, it is a good practice to wipe off any heavy deposits of that remaining 5% before applying a new thread compound.
Which makes sense.
Yeah, the reasoning makes perfect sense. You do that so you do not dilute the solid contents of whatever specific drilling compound you are about to apply for the actual operation.
But the text explicitly states that residual films do not have to be completely removed. Under normal circumstances, there is absolutely no base grease compatibility issue with leaving a thin residual film of Korr-Guard on the threads.
Which is massive for efficiency out in the field.
It's huge.
You don't have workers out there burning daylight with harsh solvents and wire brushes just scrubbing thousands of pipe threads down to bare metal. They just wipe the heavy clumps and go.
Exactly.
Except, well, wait. There is one very strict warning in the text.
Well, yes, the exception.
Right. You can leave the film. There are no compatibility issues except for clay-based greases. Here's where it gets really interesting, because throughout this entire document, Jet-Lube has been incredibly detailed about the chemistry.
Oh, yeah, they spell everything out.
We know the specific gravity, the exact viscosity, the yield reduction variables, but then it just drops this absolute rule. Do not mix this with clay-based greases, and it offers zero chemical explanation as to why.
It is a glaring omission in an otherwise rigorously quantified document. When a technical data sheet gives you a blanket exception like that without elaboration, it means the incompatibility is severe.
Workers must obey this rule.
Absolutely. We have to theorize a bit here based on the chemistry we do know. Clay greases typically use something called bentonite clay as a thickener rather than the metallic soaps used in Korr-Guard.
So what happens when they meet? Do they just repel each other like oil and water?
It is likely much worse than that. If you mix a highly complex alkaline calcium matrix with a bentonite clay structure, you risk a fundamental chemical reaction. They might literally break each other's molecular bonds.
Oh, wow.
Yeah, the resulting mixture could completely drop the base oil out of suspension, turning the grease into a watery soup that immediately drips off the pipe. Or conversely, the calcium in clay could react and lock up into a hardened cement that ruins the threads and seizes the connection.
Neither of those sound good.
No. Either way, the instruction is an absolute boundary. Do not test this exception.
Do not mix the calcium matrix with clay. Got it. So we have this olive green paste that survives boiling salt, freezing cold, and long-term storage. The document notes it is manufactured by Whitmore Manufacturing, LLC, an ISO-certified company.
Right. ISO 9001 and 14001 certified.
Exactly. And to translate that jargon, it means their factories have highly vetted, internationally recognized quality and environmental management systems. But before a single drop of this highly engineered paste can be brushed onto a drill string, it has to survive a completely different kind of pressure.
And this might be the toughest test yet.
Right. Not salt fog, not extreme heat. It has to survive international regulation.
The bureaucracy of chemistry. This is where the product's formulation proves to be incredibly strategic. The text dedicates a significant section to current REACH registration guidelines.
REACH?
Yes. REACH is a major European regulatory framework governing the production, import, and use of chemical substances.
Now, you listening might be wondering why we're talking about European REACH compliance when we were just talking about offshore drilling in the Gulf or pipe yards in Texas.
It's a fair question.
But think about the global supply chain. If you engineer the greatest, most impenetrable rust prohibitor on Earth, but a drilling rig in the North Sea isn't legally allowed to import it because it violates chemical red tape, well, your invention is useless.
Exactly. The engineering absolutely does not matter if the bureaucracy blocks it at the border.
So how do they get around it?
The way Jet-Lube navigates this regulatory minefield is quite elegant, actually. The document states Korr-Guard is officially classified as a mixture, not a substance.
Ah, a technicality.
Yes, but a vital one. Because it holds that specific classification, the final product is saved from requiring its own massive individual REACH registration.
So they found the mixture loophole, but they go even further to ensure compliance, right?
They do. The specific calcium thickeners that they use in the manufacturing process, the very thickeners holding that massive 19 to 25% rust inhibitor, are presently classified as exempt under the current REACH guidelines.
So what does this all mean?
If you zoom out and look at the whole puzzle, they have built this highly advanced product out of regulatory muzzle pieces that perfectly snap together without triggering massive supply chain delays.
That's incredibly smart.
It is. The text notes that all the other materials and oils used in the product are either currently registered or they are in the process of being REACH registered by their specific manufacturers and suppliers upstream.
Wow. It really means the formulation of Korr-Guard isn't just a triumph of chemical engineering, it is a triumph of regulatory strategy.
Absolutely.
They successfully build a heavy-duty industrial compound from a matrix of exempt calcium compounds and perfectly compliant additives. They didn't just solve the physical problem of rust, they solved the legal problem of compliance, ensuring this massive structural shield can actually reach the global markets that desperately need it.
Which perfectly brings our journey through this document full circle. We started this deep dive looking at a single technical data sheet for an industrial storage compound. And what we found was a masterclass in solving a complex problem by rethinking the very foundation of the tool.
Yeah, they really tore it down to the studs.
They did. They looked at the weak 2 to 5% oil-soluble inhibitors of the past, our soapy drying sponges, and realized the basic premise was flawed. So they moved to a robust 19 to 25% thickener complex. They took the rust protection and baked it directly into the physical skeleton of the grease itself.
And that is the invisible science we want you to walk away with today. The next time you see heavy machinery or drill pipes stacked high in a yard or miles of steel pipeline baking in the sun, think about the microscopic battle happening right on the surface.
Yeah, there are incredibly dense, highly engineered coatings fighting a quiet daily war against the elements on your behalf, standing between those massive structures and total decay.
It is a quiet war, but a brilliant one.
When you start relying on an additive to do the heavy lifting and instead make the protection the structural foundation, the whole paradigm shifts.
It really does. And I want to leave you with a final lingering thought to mull over today. Jet-Lube revolutionized this industrial grease by moving the protective agent out of the liquid and structurally embedding it directly into the thickener, the very packaging that holds the grease together.
Right.
It makes you wonder, what other temporary solutions in our world are we currently struggling with? Whether we are talking about digital data security or targeted medicine or even everyday consumer goods, what else could be radically improved if we stopped treating the protective element as just an additive we sprinkle on at the end and instead made it the fundamental building block of the system itself?
That's a fascinating question to ponder.
Think about that. Thanks for joining us on this deep dive. We will catch you next time.